All right, so here's a think aloud for practice 6 in our packets. We are going to, first of all, change this to 10 seconds for now. Even though it's not really 10 seconds, it's 9.69, which is impressive, but for just our calculation's sake that we're going to use 10 seconds. So we see that in our boxes here that they only give us 6 boxes. So we're going to have to figure out a way to make sure that we can fit 10 seconds into here. So what I'm going to do is start off with 0 seconds, then go up by 2s. 2, 4, 6, 10. And there's another box, but we don't have to use it, so we'll just color that in, okay? Now, we would like to find out how long it took him to run this much. So let's go to our calculations, sorry. So our velocity is equal to the change in position over the change in time. His change in position was 100 meters, his displacement. So from start to finish line, it was 100 meters. And it took him approximately 10 seconds to do this. So that means 100 meters over 10 seconds is that he ran it in 10 meters per second, approximately. Okay. So that means for every second, he ran 10 meters. So there's 2 seconds. And so 10 meters, our velocity is 10 meters per second. And since there's 2 seconds, this will be 20, whoops, I keep writing the wrong units. 0 meters, so 20 meters. In 4 seconds, he was at 40 meters. In 6 seconds, he was at 60 meters. In 8 seconds, he was at 80 meters. And in 10 seconds, he was at 100 meters. Okay? And we're going to assume that it was a constant velocity. So again, our time will go by 2s. And then we'll color this in since we don't need it. And so he started off he's right when when they started timing, he was already going at his very fast pace of 10 meters per second. So all the way through, he was going at 10 meters per second. Okay. And let's go ahead and solve for B before we start graphing. Okay, so B, I'm going to go ahead and change this one to blue. In B, if Usain could keep that pace, so same velocity for 200 meters is our displacement, what would be his finishing time? So that's our delta T that we're going to be looking for. So that means that he's going to start at the same place, which is the starting point, and he's going to end at 200 meters. And his velocity will be at 10 meters per second because it's the same velocity that the problem just told us. So that means that this part is going to stay the same. He was going at 10 meters for every second. Oh, this should be 2, 4, 6, 8, 10. Oh, actually, we don't know this. Okay. So in 10 meters, so our displacement is going to equal his velocity times time. We know that the displacement is 200 meters. We know that his velocity is 10 meters per second. So now all we need to know is time. Well, if we use algebra, we divide both sides by 10 meters per second. Then our time is going to be 200 divided by 10 is 20 seconds. So our last number is going to be 20 seconds, and he was going at 10 meters per second. And then in our position time graph, we're going to say he's going at 20 seconds. Okay, so that means this is 2 seconds, 4 seconds, 6. No, it's not, because we want it to go up evenly. And some of you asked if you could go up by 4s, which is totally fine. That's an 8. 12 seconds, and then 16 seconds. And so that means at 4 seconds, he was going 40 meters, 80 meters, 120 meters, and 160 meters. Okay, so because I want to go up to 200, I might want to change, I want to make sure that my position time graph is at the same place. So we're gonna go up, so here's 0, 0, why is this not working? Okay, so 0 meters, and we want this end to be 200, so we can go up by, or so 20 seconds, so we'll just go up by 4s. Sorry. So 0 seconds, 2 seconds, 4, 6, 8. No, I'm sorry. We're going to go up by 4s. 0, 4, 8, 12, 16, 20, and then 24. This is seconds, okay? And then our position time, since we want to go up to 200, we can go up by 40s as well. So we have 40, we have 80, 120, 160, 200, 240. Okay, so we went from 0 to 200, because this is our blue. So 200, it took him 20 seconds to get to 200. So we're going to go ahead and draw our straight line from 0 to 200. Okay. And then for the part A, he went from 0 to 100, which is probably about here somewhere. Okay. So there's part A, and part B is here. Okay. So this is same velocity. The time, let's do this in pink. So the time here from A to B has doubled, and then our displacement, sorry, here, our displacement here has doubled, so double the displacement. Okay, so when we make our velocity time graphs, we want to make sure that we keep the intervals the same. So we'll go 4, 8, 12, 16, 20, 24 to match. And we can go 5, 10, 15. Okay. The velocity for A is 10, and it goes up to 10 seconds. So we want to make sure that we go 10 to 10 seconds. And so this is our area, our displacement. So displacement for A. And then for B, it also happens at 10 meters per second, but it's happening for 20 seconds. And I'll just go the other way so that we can see both. And so this is the displacement for B. Okay. And so you're asking, how does it relate to proportional reasoning? Well, so from A to B, we always want to think from A to B. So from A to B, our velocity stayed the same. So when it stays the same, we'll multiply it by 1. Okay. Our delta x from A to B, they told us that it doubled. And so they want to know what happened to the time. Okay, so our velocity stayed the same, and our displacement was increased by 2, a factor of 2, so it doubled. So in order for this to be true, it needs to be 2. And since this is what they were looking for, this is what the question was asking, it's going to go in the variable spot. Okay, so this is going to be our delta t. And the coefficient that comes with delta t is 2. The original value of delta t was 10 seconds. So we'll say 10 seconds. So 2 times 10 seconds is 20 seconds. So this is our new value. Okay, that is it.